So one is that LU, the dot product of LU and F, is the expectation of Y from PU of F of Y. And the reason is you just write what is this, right? We can write it as sum over Y of QY, QY, PUY, F of Y, right? So just divide and multiply by QY. And similarly, so L comma F will be the expectation of F over P. And yes?
Can I ask a very simple
No.
What is PY? P is your model, right?
P is a probability distribution.
And PU is also probability distribution.
Yes.
And P is also the class.
No. P is just P is okay. So P, I think of it as a probability distribution that is obtained by a convex combination of. So maybe a better way to write it. Okay, so let me fix this. Yeah, I think you're right that my notation. So P is that a good term? No, I don't know. Let's write it as sum over mu u over u. Is that like so? So P is this convex combination of probability. It's a probability distribution. So let's just give our. We have some space R. So P is a probability distribution over R, which is obtained by first sampling U according to some probability distribution mu, and then sampling Y from PU.
Okay, so it's like a conditional distribution.
Not conditional, no. That's just a probability distribution. That's the planted distribution. So you take a random signal, say U, and then you take a random observation from PU. Okay. So P of Y is just P is just a probability distribution. So P of Y is just P of Y is just the probability of Y. And if we think of P as if we think of P as a function, then you can think of so you can think of P as also as expectation of P of U, right?
I think you mean F of Y in the square, the known square.
The known square. So F of Y, or like I wrote F of Q, I meant like Y distributed according to Q to the random variable Q. So part of the reason I wrote it is because I know myself. I'll probably use this shortcut at some point, so I might as well introduce it. What?
Then no E.
No, expectation.
You can't have it both ways.
What?
You can't have it both ways.
Is that, no, that's good, right? Expectation of F over the random variable Q, right? Is that not valid?
Either you put the expectation or you put the F of Q, but not both.
Okay. Expectation. I just want to make sure that I know what the expectation is over. So Y, this is the right thing to do. Yes, F of Y squared.
Thank you.
Okay. So the second thing is say the norm of L squared is the dot product of or we can write it this way, right, because of LU, LV, right? So L is the expectation of LU, right? So the norm of L squared is, the dot product of expectation of LU, expectation of LV. So it's the expectation of UV, the dot product of LU and LV. Okay? And another thing is that, say, LU minus 1, LV minus 1. So if we open it up, we'll get LU. So we'll get we'll get LU LV. Okay. So LU minus 1, LV minus 1. You'll get it's LU LV minus LU1 minus LV1. plus 1, 1. Right, so this is the expectation of 1 according to the probability distribution PU. So this is 1, so this is 1, this is 1, and this is obviously 1. So basically this just equals this minus 1. And generally also you can similarly L minus 1 squared is just norm squared minus 1. Okay. And maybe one more nice way to think about this low likelihood ratio is we can write the following. So the norm of L is the maximum. Okay, so I really like this expectation. I'm sorry, I just like this thing. So I'll write this. I don't know. I like this thing. So a maximum of the expectation of FP such that the norm squared, which is the expectation of FQ squared, say, or I think we can write it even, maybe this is nice, norm of L minus 1. Okay, so this is basically, if you think about it, what is L minus 1 squared? You're trying to find the maximum of some function such that the random variable, you're trying to maximize the bias, the difference between P minus Q, while keeping the variance, say, under Q, or yeah, maybe this would be, I think this might be the variance of F. Let's, yeah, might be here. It would be just exactly the variance of F, such that the variance of FQ equals 1. So that's so basically the L minus 1, the norm of L minus 1 really captures by how much we can distinguish P from Q. And generally this is because what is L minus 1, right? L minus 1 F is really just the expectation of, right, it's LF minus 1F, which is the expectation of F under P minus the expectation of F under Q. And then L minus 1, maybe I'm norm. Right, and L minus 1F is smaller than, yeah, so it should be the, yeah, I never know if it's the, so L minus 1. Okay, so maybe instead of, so here, maybe I should say expectation of F cube, but it should be also with the variance.
It's the same, because the position is 0.
Yes, yes. So, yes, so the optimum will be the expectation 0, so you get a variance. So basically, L minus 1 squared captures, yes. So basically, L minus 1, and the best F to do it would be, L minus 1. This would be the maximizer. And this is also, and another way to say it is that this is also the same as, this is also known, this quantity is also known as the chi-square divergence of P and Q. So basically this is, so this has a very nice kind of operational meaning. You're trying to distinguish between P and Q, then you're trying to find a random variable, let's say, normalize it to have, variance 1, and you're trying to maximize the difference between P and Q. Okay? So now, here is, and again, one of the reasons why I'm going through all of this is we are going to, tomorrow.
Aren't you saying basically proving Newman person here? Like
What?
Well, you are basically saying that the best function is the likelihood ratio itself.
Yes,
So it's
yes.
kind of,
Yeah, it's basically proving, except like, this is about distinguishing bias versus variance, which in principle, maybe one way to say it is like the expectation could potentially come from a very low probability event. So it doesn't necessarily mean that there is a good, maybe that's a good point to make. So maybe I'll make it more. So here is, and by the way, what I'm going to do. What I'm going to do tomorrow, I'm going to go over all of these and then define something known as the low degree likelihood ratio, which will be kind of the low degree projection of all of those things, and a lot of those things will carry over. And one intuition that we have is that basically low degree likelihood kind of captures, and I'll say in a second, kind of captures, but not exactly. This likelihood ratio kind of captures the ability to distinguish between P and Q. I'll say in a second why not exactly. And the low degree version kind of captures the ability to efficiently distinguish between P and Q. But let me, so here is a theorem. I don't know if it's worthy of theorem. Let's give it, but let's be generous. And basically it says the following, if L, if L minus 1, which is the same as L minus 1, is less than little of 1, then there is no weak distinguisher. And if L, here the minus 1 really doesn't matter because we just look at, if it's bounded, then there is no strong distinguisher. So here the errors cannot go to 0. Here the errors cannot be bounded away from 1. So this says basically if the norm of the likelihood is small, then if the norm of the likelihood is small, then then you cannot distinguish. But going back to Florent's point, it's not an if and only if. So before proving it, let's just say it's not an if and only if. And the main reason is you could have the following type of. So where is my nice? Yes, so you could have the following thing. So suppose that you have that this is L. Say this is L. It looks like this. Basically, I don't know. This is very small values, and then you have some slight bump. So basically, you have some value y star that say p of y star is a 2 to the 0.1 m, but q to the y star is a 2 to the minus m. So in this case,
just to make sure, the little one is in the size of the system or in the number of observations?
Let's say right now we're not even talking necessarily about system observations. So the size of the input or some parameter. There will be some parameter going to infinity, and and this is it. Now suppose even like very simple thing where basically the two distributions are basically the same, or let's say the two distributions are are the same. So the likelihood ratio, the two distributions are basically the same, except that there is this y star which has exponentially small probability of appearing in both, but it's different, right? It's right. So in this case, you cannot distinguish between the two probability distribution because it's an exponentially small event. But the contribution, this will be very big, right? Because you get like here the likelihood ratio L of y star is like 2 to the 0.9 m. So L star will be at least just the contribution from this particular y star will be you get 2 to the minus m times 2 to the 1.8 m. So 2 to the 0.8 m, right? So you could have like the likelihood ratio is exponentially large, even though you cannot distinguish between the two, and this happens because the exponentially large really comes from a very, very low probability event. So this is not an if and only if. Interestingly, these kind of examples seem to sometimes more disappear when in the low degree version, but generally, like, so this is a way to rule out distinguishers rather than to demonstrate that they exist. Okay, but let's prove this theorem. Again, I think. How much time do I have? What? 0?
So we have time to prove the theorem.
Yes, it's a yes. 5 minutes. Yes, so let's see. Okay. So I wanted to show something better than just proving this theorem. So can I take 5 minutes?
Yeah.
Okay.
I mean, even 10 if it's
okay.
It would stop
If it's
being
interesting.
after that.
Yes, I wanted to talk about the spiked matrix problem.
Well, then you have half an hour.
Yes. so I think you guys can believe me about this theorem, right? Let's leave it to, for an exercise for the scribe. Yes. Yes. Exercise. I always meant it to be an exercise. So yes. So now that we have seen this theorem, so now let's talk about the spiked matrix problem, because that's more interesting. So there, the distribution looks like that. You have lambda v transpose plus z, where z is normal with just a normal matrix, n by n matrix. V is, think of V as a random, here let's think of V as n0i. Okay, and so this is the signal to this is a signal to noise kind of problem. Lambda is our parameter, and now you can do you can define, right. So what is say LV of y given some observation y? So let's say observation is of this form.
So maybe just a comment for
Mm-hmm.
for the others, that this model is exactly the same one that Remy and Julia were also mentioning in their lecture, right?
Mm-hmm.
But not in this context of hypothesis testing, but just
Yes.
for people to have the context.
Yes. So L of y, it's you basically can think of it as the following. So one way. So you can do the computation. I'm going to ignore some constants in front of it, but it comes out to be L of y comes out to be minus so if y was of that right, so if y was of this form, it will be let's see how will I write it? Okay. So if y what was of this form, it's minus. You want to write it as minus y minus lambda VV transpose, right? Squared. That's the exponential, because z is Gaussian, so you write it as this. And this basically will come out. So the main point here is that this will come out to be exponential in lambda y VV transpose, and some parts that are independent of V. So what we get is that LUY, LVY, and if we take this expectation, so this is again some calculation which I want to somehow go a little bit, but I can go with the people that write the scribes and go slower. So what we get is that this just comes out to be the expectation exponential of lambda squared, the dot product of UV squared. Okay, so if you have LU and LV, okay, so just some kind of intuition, then what you get here is that the likelihood of y according to u is scaled like depending on its dot product with y is a matrix with u transpose likelihood with this lambda. The likelihood of v according to of y according to v is scaled with exponential of lambda of y v transpose. You take expectation over the null model of y from the null model, which is just Gaussian, and so you get something that looks like exponential of lambda squared times the Gaussian, and lambda squared times the Gaussian, the expectation of e to the lambda squared times the Gaussian, and the expectation of that is e to the lambda squared times the dot product squared of the dot product of u transpose and v transpose, which is the dot product squared of y in u and v. Okay, so now I just want to get to this corollary and send us to dinner or to pre-dinner break. So you can do these calculations, and this comes out to be this case. Now just remember that this norm of L, that was expectation over UV of LU comma LV. And now we have calculated what it is. Okay, so now basically what do we see? We see that the norm of L squared is expectation over UV of expectation over UV of e to the lambda squared UV squared. Okay, so now if you have two random unit vectors in n dimensions, then UV is basically distributed like n0 1 over n, except that it cannot go it cannot go higher than 1, right? But it basically is distributed like that. So this is, and again, I'm ignoring. I'm only going to care about whether the norm is bounded or goes to infinity. So I'm going to ignore you know, that there is some kind of constants before of this, especially since I don't remember them. So, so we are going to, so this is going to look like lambda, so this is going to be like the integral of, you know, lambda squared x squared minus, right, the Gaussian, but with this. Right, because we have 1 over n variance, so this is going to be our, so this is going to be this quantity, right? And now what the nice thing that you can see is that it goes to, you know, that if lambda squared is larger than n over 2, then this will go to infinity. And if lambda squared is smaller than n over 2, this will be bounded. And if people actually want to calculate this thing, there's actually like, and with the right constants, it actually is 2 pi 1. This I copied from a paper. I don't, yeah, but you can do the calculation exactly. But the main point here is that you can see that there is a threshold where, if we do the math, then that corresponds to lambda being smaller than, so the threshold is at lambda n over 2, square root lambda being square root of n, square root n over 2, where basically here you get that here you get that the likelihood that this goes to infinity, and here you get that this is bounded. And in fact, this threshold is actually where you can and where you cannot recover it. And maybe I'll just say that you have, there is an algorithm actually exactly at this threshold. And the algorithm is you basically just take y plus y transpose over, say, square root t. Square root 2. In the null model, you get the Gaussian. In the null model, you get the Gaussian orthogonal ensemble, the GOE. So in the null model, if it came from Q, it will lambda max will be 2 square root n. If it came from P, then you can show that lambda max will be something like it's going to grow. It's exactly in the GOE. Basically, you kind of do the math. So because you divide by square root 2, then the lambda will the effective lambda becomes like square root n, and this is basically GOE with a spike. And it's known that the spike increases lambda max exactly when you spike it with more than square root n, with more than 1 times square root n. And the eigenvector is actually going to be correlated with the spike. So once you go above, so in the GOE, the lambda max is 2 times square root n. And if you spike it with lambda square root n, then the new lambda max is at least lambda plus 1 over lambda, which is more than times square root n, which is more than 2 exactly if lambda is larger than 1. So it actually turns out that this prediction is actually precisely right for this model, and also this model doesn't have a gap. At the moment where you get when you actually can solve it, you can actually solve it using an efficient algorithm. And I think this is a good point to stop.
Okay, so since we're a bit over time, I will not allow question today.
But I'm here. I'm staying here. Yes.
However, we have a very important decision to make.